Hi, this is Mrs. Vrobel. This is part 5 of covalent bonding chapter. So we've talked up to this point about how to name covalent compounds. We've also looked at dot diagrams. How do you identify if a bond is polar or non-polar? Now we're going to look at what we call solubility. And in order to understand solubility, we have to look at what kind of interactions are happening between the different molecules. Now I have a little beaker here that has a combination of oil with blue dyed water. So I added color to the dye. And just to show you something interesting here, so I'm going to take the blue dye that I have and I'm going to add a drop of it. And when I do, watch what happens. So notice the drop of dye, it doesn't stay in the oil layer, which is on top. Instead, it sinks to the middle section where we have an interface between the blue dye and the oil layer. Now the other thing I want to show you is I have some sugar here. First, let me mix this dye. So notice how the dye goes into the lower layer. What I'm going to do is I'm going to take some sugar, and sugar is a non-electrolyte, and I'm going to sprinkle some, see my sugar? I'm going to sprinkle some of it on the, oops, there we go. Okay, notice how the sugar, it doesn't stay where the oil layer is, it goes directly to the bottom, okay? And just to prove it to you, I'm just going to keep stirring here. And I don't know if you can see, but the sugar is staying in the water layer. It's not going anywhere near the oil layer. Okay, so what does this mean? Well, we need to talk about what is dispersion force. So a dispersion force is actually a momentary dipole. It's like for a split second. It's not a permanent dipole like between a covalent bond where you have an electronegative atom and a less electronegative atom. Notice that it's also called London forces, so it's the same thing. It's typically found through nonpolar molecules. So we're looking at atoms that have the same electronegativity. There's very little difference in electronegativity between them. You may see it in nonmetals. So notice that we're talking about essentially bonding to the same atom, like H2, O2, P4, okay? These are all nonmetals, and there's no real electronegative difference, so they're considered nonpolar. You can also have compounds like CH4. So CH4, there isn't enough of a electronegative difference between carbon and hydrogen, so it's almost no polarity in that bond. And no CO2. So even though there is an electronegative difference between carbon and oxygen, it's the way the dot diagram is drawn. So remember we had two double bonds on either side with the oxygen, and they essentially cancel each other out. Okay, now as molecular size increases, so does London forces. What does this mean? That means if you go down the periodic table in a group, the London forces are going to be stronger towards the bottom than they would be on the top. Now these are very weak attractions because there isn't overall polarity in the molecule. So notice that there's low melting and low boiling points because of this. You will find some solids have very low melting points, but you may notice dry ice sublimes, so it goes from a solid phase to a gas phase. If you still have mothballs at home, some people still use mothballs, you may notice over time the mothballs actually get smaller, so they go from a solid phase to a gas phase. Also, gasoline will have a situation where you're going from a liquid to a gas. Okay, now what does this chart mean here? Okay, So notice that at the top here, we have a series of compounds that are bonded to hydrogen. And what actually is happening is oxygen is at the top of the group and the bottom of the group is tellurium. Here we have HF, and notice everything in red. You're going down a group, you end up with HI. So fluorine is at the top of the group, iodine is at the bottom. Here we have NH3, that's at the top of the group, and then antimony is at the bottom. And then lastly, we have carbon at the top, and then we have tin at the bottom. So notice that these three compounds over here, they have very high boiling points, and part of the reason why is they are more ionic in character. So because they are more ionic in character, they actually have a greater attraction with each other. So it's harder to get them to go from the liquid phase to the vapor phase. Now, down here, these compounds have something else going on. They're less ionic, but they have a stronger dispersion force. So their attraction with these self are greater because they have an instantaneous dipole, and that attraction is strong enough to help them have a higher boiling point. Now notice that as you go down a group, these attractions are weak, but they become strong again when you get to the very bottom of the group. Okay, here we go. Now, if you do not have a nonpolar compound, what if you have a slightly polarized molecule? You have what we call dipole-dipole forces. Now notice that you have to have a polar molecule, so you have to have enough of an electronegative difference between two atoms that are bonded to each other. So notice you could have HCl, H2O, NH3, SO2. Those are all considered polar molecules. There's something special. You can have what we call hydrogen bonding. Now, this is a misnomer. We're stuck with the way it was named. It is not a chemical bond, okay? So not a chemical bond. Please remember that. It's an attraction. So because it's an attraction, it's a little bit different from a chemical bond. Now, what this means is you have to have hydrogen, and in that compound, that hydrogen has to be bonded to oxygen, nitrogen, or fluorine. If you don't have these series of atoms in the compound, it's not going to be hydrogen bonding. It's just going to be dipole-dipole. Okay. Notice that HCl is a dipole-dipole attraction. It is not hydrogen bonding. Okay. Now what happens with hydrogen bonding is you have a slightly polar bond. So there's more electron density near the greater electronegative atom, and the positively charged side is towards the hydrogen atom. So the hydrogen atom finds another molecule that has a negative, slightly negative charge to it, and it attracts itself to that side. And I'll show you a picture of that here. Okay, just further information. The reason why we have the environment that we have. Okay, we would not be on this planet without water. Water is essential to life, and they're pretty darn sure because they've looked in other parts of our solar system. And because water has a very high melting and boiling point, so notice we have a melting point of 0 and a boiling point of 100 C. That sustains life. And reason why is we have hydrogen bonding. So we have hydrogen, we have oxygen, and they have a strong attraction with other water molecules, which causes it to have this high melting point, high boiling point. Now, if you look at these other molecules, H2S, H2SE, H2TE, they all have lower melting points and boiling points because they do not have hydrogen bonding. They have a weaker attraction with each other. So because of that, they have a lower melting point, lower boiling point. So hydrogen bonding is a very strong attraction within molecules. Remember, it's not a chemical bond. Okay, what does this mean? So when we look at dipole-dipole interactions, notice that the amount of energy that you need to add in order to overcome these attractions, it's 20 kilojoules. London or dispersion forces is much smaller. It's only 2 kilojoules. So notice that the attraction of molecules that are nonpolar is very weak compared to dipole-dipole interactions. Now, up at the top here, we have covalent bonds, ionic bonds, and hydrogen bonds. So the strongest bond, and let me talk about that here. We have what we call covalent network solids. Diamond is an example of a covalent network solid. And these are unusual molecules. These tend to have the highest melting and boiling points. Now notice that ionic solids are after that. So ionic solids are only 800 kilojoules. However, right after the strength of ionic bonds comes hydrogen bonding. So remember, we have to have hydrogen bonded to nitrogen, oxygen, or fluorine. And notice that it's 40 to 70 kilojoules. If you don't have hydrogen bonding, you have dipole-dipole attractions, which is 20 kilojoules. And then the weakest is the nonpolar dispersion forces. Now for metals, metals have an even stronger attraction with themselves, okay? So they have a higher strength with their bonding forces. Okay, so you may hear the term like dissolves like. That's a good rule of thumb. So what I just showed you here is that sugar will not dissolve in oil, it'll only dissolve in water. Same thing. So anything that is polar, once you identify its polarity, you can determine whether or not it's going to dissolve. Now, just to let you know, polar solvents will also dissolve ionic solutes. So if I was to put salt in that beaker that I just showed you, it would dissolve in the water, not the oil. What does that mean? If you have a nonpolar solvent like oil, it is better at dissolving nonpolar solutes. So you need to identify whether or not a molecule is ionic or polar or nonpolar, and that'll help you to determine whether or not something will dissolve in another substance. Okay, so here we have water and ammonia. Now if you look at water, we have hydrogen bonding. So we have hydrogen bonded to another oxygen. And ammonia, we actually do have hydrogen bonding also because we have hydrogen bonded to nitrogen. Now notice how the water molecule arranges itself so that the positively charged hydrogen, and remember this is a slightly positive charge, it aligns itself with a negatively charged nitrogen. And that typically happens when you're trying to dissolve something. Okay, here we go. So I have a series of solubilities, and notice I have water at the top, paint thinner at the bottom. And the question is, these sets of compounds on the left, do they dissolve in water or paint thinner? Well, if you look at magnesium chloride, notice I didn't say magnesium dichloride, I said magnesium chloride. That's a clue to tell you that this is ionic. So ionic compounds, if you had to guess, do they dissolve in water or paint thinner? Hopefully you said the polar water. Now, here we go. This is P4. Do you remember from the slide, what type of compound is it? Okay, P4 is nonpolar. So, if you had to guess, which type of liquid would it dissolve in? Okay, so hopefully you picked paint thinner. Okay, so here we have an interesting compound. We have C2H4OH2. Now, because there's oxygen and hydrogen, what type of compound, what type of attraction would it have? Okay, hopefully you said H bonding. Notice it's not a chemical bond. So it should dissolve in water. Okay, here we have CH3NH2. So the question is this going to dissolve in water or paint thinner? Well, notice there's a nitrogen and it's also bonded to hydrogen, so it also is H bond. So it should dissolve in water. Okay, this is the last one I'm going to do, and then you're going to do the next three on your own. So make sure you do K2S, Br2, and HCl. Okay, so we have C8H18. The question is, what kind of attraction would it have? Okay, so hopefully you said dispersion forces. So if it's dispersion forces, what type of solvent is it going to dissolve in? Okay, so hopefully you said paint thinner, and you would be correct. Okay, so you should practice the next three on your own, and don't be surprised if you see that with the video assessment.